All right. Good morning. Tēnā koutou katoa. My name is Shane Clark. I'm the General Manager here at Nuralite. Welcome to our last webinar for the year. You can probably tell it's December. Thank you very much for all that have joined us. All right. So on the back of last week's webinar, we were talking about external insulation. We put a quick poll out there last week and said, is anyone interested in learning about the new H1 that has been raised by MB? And we got an overwhelming response. So we very quickly last minute threw this webinar together. So it may not be as polished as the normal ones, but we managed to grab Jason Quinn from our last webinar as well. So thank you, Jason. For those of you who don't know, Jason is the manager at Sustainable Engineering, and he got bored of being a rocket scientist at NASA, so I thought he'd come to New Zealand and be a building scientist. A bit of a challenge. And I also have Peter Mills with me on the panel, who's our internal technical consultant, who plays with our Bracker software for working out our condensation points for roofs and things like that. So we'll talk to him later about what he's come up with. Today we want to obviously talk about the impact that the new H1 requirements have, particularly around the schedule method for roofs. We're going to cover what the new H1 requirements are. Hopefully going to cover some of the possible unintended consequences of the increased insulation in our roof. And we want to obviously give you what we think is our best practice when it comes to warm roofs, flat roofs, skillion roofs, etc. So those are the things we're going to cover today. We're going to start with a bit of a poll. So by all means, get involved, get the keyboard going, and just keen to learn when you think you'll be designing to the new H1 levels. Give you a couple of minutes to populate that. All right, thank you for that, folks. So we scheduled for around about 30 minutes, and then we're going to have a bit of a Q&A at the end. So if you've got some questions, by all means, feel free to chuck them into the questions box, and we'll, if we get a chance, we'll go through and answer those at the end. Usually we get a lot of questions, we don't have a chance to answer them all. But what we will do is we'll send a recording of this webinar to all the people who have signed in, and you'll get a copy of, obviously, of the webinar, and also get a copy of the Q&A that we've covered as well. All right. So without further ado, we'll start with you, Jason, and we're going to talk about obviously roof insulation, the new revised H1, particularly around the schedule method. And I guess the first slide is we've got some new zones.
Yeah. So we'll talk about H1, AS1, and AS2, right? So both for homes and for non-residential buildings, just the roof stuff. So so we finally have climate zones that make sense from a actual climate point of view. So it's colder in Queenstown than in Nelson, and there's some variation across the country. It's quite funny because all these climate zones were actually developed by NUA 20 years ago or something, right? Or 15 years ago. And then what they did for this particular version of the building code is they tried to figure out what's the fewest they could get away with that actually made sense from a physics point of view in terms of energy use in buildings, and ended up with this. So it's quite a good thing. So 6 climate zones, and it even includes, Chatham Island, which is great.
Yeah, all right.
Yeah.
So there was 3 originally, wasn't there? We had 3.
Yeah, we had
originally. Yeah.
3, and so they developed the 18 zones, and we dropped it down to 3 before the last building code update, which was for insulation. And the reason they did that was there was a lot of commercial work done to try to push for that, because the South Island is a relatively small consumer base versus much of the North Island because of population. Sure. So anyways, but it just doesn't make sense, especially when you're trying to save energy across the country. All right, so we've got 6 climate zones, but the funny thing is for H1, AS1, the schedule method says you have to use R6.6 across the entire country. So we should all take advantage of this to make fun of MB when we get a chance, because they enjoy it, and as long as it's well meant. So we've gone from roughly an R3-ish kind of roof to R6.6, so roughly a doubling of the insulation requirements, because insulation is roughly just due to thickness. So it means your roof insulation's got twice as thick now, unless you increase the performance of insulation.
Wow. Okay.
And then if you think 6.6 for buildings is a big change, look at commercial buildings, which have gone from very, very little insulation in our large buildings, R2-ish, up to R7 down in the South Island. So, and even, twice that effectively in our warmest climate zones. So a big change. Now, both these changes were done to try to hit about 40% heating energy savings in homes, and for large buildings to hit about a 20% energy savings. So a lot of that was due to this roof change. And we could argue as to why they made just the roof change versus wall changes and other things, but MB has basically said they just felt it was something that was achievable for the New Zealand market to do this. And it's certainly we've done a lot of buildings with this kind of R values. So
last week we talked about walls being sensitive. Use that PC word, sensitive. Are roofs not as sensitive, or how can we sort of exceed?
Yeah, to some extent they're more sensitive, but they're a little bit easier to deal with. So when our most common construction, the one that probably MB had in mind when they laid this out, was a vented attic roof, or what Peter typically calls a cold roof assembly, where you've got a gypsum board ceiling or some other nice air control layer in the ceiling, and you've got insulation on top, and then above that it's ventilated to outside air. So the important thing, and the next slide is a good one to get into. Sure. It's all about keeping that warm, moist air from getting into that attic space or to get above the insulation, because once it does that, unless it vents out very quickly, you get condensation. And if the airflow rate's too high, you get the condensation, even if you have good venting, right? So it's really common if you crawl around in attic spaces in colder climates, like in Queenstown, and you look at a normal vented attic roof, which has got a good gypsum board, well-stopped gypsum board layer, but they put a can light in the bathroom for some crazy reason, which means they've got a big hole in the ceiling in the bathroom. Yeah. And you'll see mold if they've got a rigid sarking, like an OSB sarking under the roof, because they've got a asphalt shingle roof in Queenstown, there's a few houses like that. We'll often have mold underneath on that asphalt, on that OSB, because there's moisture coming up to that roof and it's hitting the underside of that roof and condensing and causing condensation, causing water and then mold. So this is pulled out of the insulation guide that you guys talked about from last week, but it's exactly applicable to roofs, right? So pretend this is a roof instead of a wall, because it looks like a roof in this picture. And you've got warm, moist air inside the building. And if it can get up and go into the insulation layer, then you can have a problem. But you've got this wrap layer, this water air vapor control layer, the green one, which is keeping that moist air from going into that insulation at a high enough rate that it causes a moisture problem. And then any moisture that does get through, because it's ventilated above the insulation, can ventilate out of the building safely without an issue. So that's kind of the main thing. When you go to these high R value assemblies and roofs, it's really important you control air control. That's like the main thing, is make sure you don't have air leaks in that ceiling assembly. If you've got big air leaks, it actually doesn't matter what kind of insulation you got, you're going to have a problem. So, and the more insulation we put in, the less, I guess, think about when you have a wall that's better insulated, you're saving money because you're not putting as much energy through that wall or roof. And because you're putting less energy through it, there's less drying potential that occurs in that insulation layer because it's thicker. So the same amount of moisture that used to be okay, like you got away with it before because it was fine, you didn't get away with it. It was actually good design. Now, if you don't have better air control, you're going to have moisture problems you didn't have before. So in Brian's talk, MB talked about that quite a bit with their unintended consequences, which I never did count how many times they said that, but I'm sure it was over 20 times. So, all right.
Perfect. Excellent. Thanks for that, Jason. Obviously, we'll chip in when we move on to the next section. But what we've got now, we've got Peter Mills, who's our internal technical advisor, who's going through a couple of roof assemblies that he's been working with. He's used his Braca software to come up with a couple of ideas, and this is some suggestions and some considerations from our perspective on things to look for when you're designing your new H1 compliant roof. So welcome, Peter.
Hey, thanks, Shane. So with these calculations, we've considered a range of different roof constructions that you can use. It doesn't encompass everything, and there are slightly different ways that you can do it, but these are mostly our acknowledgements of popular ways to do it and suggestions of how these can work and how they should be done. So if we move to the first slide, we've got pretty much the standard way that New Zealand houses with attics are constructed. You've got your jib, you've got your framing above that, and then you've got insulation between that framing and above it. This still works under the new kind of requirements. You're probably looking at about 250 mils of insulation, and it works provided there's good ventilation. If there isn't good ventilation in this roof, there's a very high likelihood that there's going to be condensation. So that's a pretty critical aspect of it.
And what sort of insulation have you used for this calculation, Pete?
So we've used a high performance lofted insulation. So a lot of designs and constructions at the moment are using very standard lofted insulation, which has a lambda value of about 0.04. And lambda value relates to R value. So the less lambda value you have, the better. So what we've used for these calculations, wherever there's that lofted insulation, is a high performance one. So if you were to use the kind of standard lofted insulation that people tend to use, in this build-up alone, you'd be looking at about another 30 or 40 millimeters of it. So you'd be going from a build-up that's about 260 mil to about 300.
Yeah, right. So in this build-up here, it's obviously very important to control the airflow to make sure you've got enough drying capacity.
Yeah, and that's what the gypsum board ceiling does that you just got in there.
Yeah, nice.
Okay.
Makes it a little difficult to walk on the rafters if you ever wanted to use that space, I guess, if it's all covered with teddy bear stuffing.
Yeah, it was previously difficult to do this. Now it's going to be worse still because now there's going to be a layer of about 100 to 150 mils of lofted insulation on top of that. Okay. You can buy little standoffs to kind of get that space back, but that doesn't really make as much sense as the next slide, where you're actually getting that whole cavity back by putting that insulation into the rafter assembly. So what we've got here is what we call a hybrid warm attic roof approach. So if we look at the diagram here, there's a bright green line for the vapor blocker layer as part of that wrap. And then we've got a PIR, high performance rigid insulation above that. So that's going to do the bulk of the work here. And then below that, you've got our high performance lofted insulation to make up the rest of that R value. So all of this is basically sitting underneath the roof. And because of those two wrap layers, there's no opportunity for condensation. So there's less reliance on good ventilation in that space and just better control of it.
Okay. So what we've got here is we've got a conditioned space within the attic. We also have a drying capacity above the outer layer of insulation, right? Which we've touched on is pretty important.
Yeah. What we find is this conditioned space is actually better for mechanical ventilation as well, because there's an opportunity for condensation within that system, just because it's all conditioned. With this one, you're already looking at a thinner insulation build overall. That's majority due to the PIR, but it is actually because that high performance layer isn't being broken by the timber. Because in the previous one, you would have your high performance insulation and you've got these timber members breaking it up and actually compromising the performance of that material. That doesn't happen here. It's unbroken, which actually this build-up lends itself also to connecting with warm walls, because that green wrap layer can actually connect to your wrap on your walls, and the insulation can do so as well. Whereas with that previous assembly, you're going to have a really hard time doing that.
Sure. Okay, and then onto the next slide, which is obviously right in our wheelhouse, flat roofs.
Yep, so we thought we'd start off with our least favorite assembly at this point. So this is a cold membrane roof. We are of the opinion that these should not be allowed anymore. They were already difficult to design and install without problems. Now they are going to be nearly impossible. With this kind of build-up, it is very critical that there's adequate ventilation. And with the build-up that we're looking here of about 260 millimeters of insulation, when you've got things like nogging to the underside of that plywood, it's going to be really, really difficult to get that correct airflow. If there's not correct airflow, it turns to custard. There's a lot of condensation that's going to form under there. It's going to drip into the lofted insulation, reduce its performance, cause all sorts of issues. So yeah, avoid this at all costs is our advice.
Yeah, like Jason was mentioning before, if we've got airflow above the insulation, we're okay. But we do know from our experience that it's very, very difficult to get adequate airflow above that insulation layer. because it's rammed up so close to the surface of the plywood. And I guess the other thing is with a flat roof, you just don't have that that thermal drive because you have no slope for the heat to rise. So
yeah, it's in practice, it's really bloody hard for the poor builder, right? It's easy for designers to draw a roof with a venting and say there's a mushroom vent 40 square meters, the way the specs say, right? It's easy to draw that, but the poor builder, when he's putting in, he's got to put blocking in at the edge of the sheets. And then, you know, there's a skylight somewhere that causes blocking problems. It really pushes the risk and the difficulty onto the builder, and I don't think it's appropriate anymore.
Yeah, and typically you'd have timber running 400 centers both ways. So you're creating these little cells. So you'd almost have a vent every 400 millimeter square, which would have a unique look, I guess. Yeah.
I guess what's probably important to mention here is actually the build thickness, because a lot of times when flat roofs are selected, the height and the build of that roof is really critical. In the previous assembly, I think we were looking at about 340 mils thickness. In this ideal scenario, the warm roof, we're only looking at about 320, 315. And that's because we're able to use an unbroken high performance PIR layer. So there's no compromising of that thermal performance. So we've only got about 140 mils of PIR, and that gets you the new H1 standard right away. And then all you have to worry about at that point is getting the correct structural framing underneath it. If you don't know about warm roofs, we're probably not going to explain this kind here because there's a bunch of other webinars where we've talked about it at great length. I don't really have anything else to add about this one.
No, that's a good point. I mean, if you are on the Nuralite website and you're looking to design and specify a flat roof, it is almost impossible for you to specify a cold roof from our website now. We are intentionally leading you down a path to specify a warm roof because over a habitable space. I mean, the only place we see a cold roof is, you know, a dog kennel or a bus shelter perhaps. But apart from that, we're strongly directing people down the warm roof route.
Yeah, I do want to make one point is regardless of which vendor you pick for warm roofs, that green layer where you've got an air vapor control layer right there on top of that outside ply layer, that's a really, really important layer, and that should be a fully adhered layer. There are still a couple warm roof suppliers that aren't necessarily requiring that in all the climates, and in my opinion, it should be required in all the climates. Yes. So just be aware of that. So you guys have a bit of an advantage there, and maybe you didn't want to mention it.
Yeah, no, very, very important. As Jason's previous slide, he showed us the building science slide there. We're talking about stopping that warm, moist air rising up into the structure, into that cavity, and that's what that green line does. So, I mean, in our case, it's actually a full aluminium foil vapor blocker. So it's not smart. It doesn't breathe one way and go the other way. It does absolutely nothing and just stops everything.
which is appropriate below a PIR layer.
Yes.
So it's the right thing to use.
Yeah.
So that's fine.
Yeah.
All right, Pete, you got a solution for some skillion roofs there. I've actually got a question coming about skillion roofs, so we'll be watching intensely. So if we go to the next couple of slides there.
Yep. So this is a kind of cathedral ceiling, I guess is what you'd call it. And this is the traditional way that you'd do it. You'd have your exposed rafters, some plywood or sarking that would be visual, and then you've got your high performance bats in that void there. You'd be looking at about 270 mil of that in this case. You'd have your wrap after that, and this works because the roof batten above that wrap allows the system to ventilate. It's pretty wieldy, like you're going to have about half a meter for this build up if you can see the little numbers here.
Right.
So there's a more ideal way to do this.
Yeah, I didn't actually see that number, Pete. That's half a meter thick roof.
Yeah. Yep.
Right. Okay.
Whereas.
So what's your idea?
Well, the next example cuts down by at least about 100 mil. So this is the Gerard Thermocore roof that we're looking here. Effectively, that top roof cladding could be replaced with a range of different options, but in this case it makes sense for us to do roofing tiles here. So what we've basically done is we have replaced that high performance bats with a high performance rigid PIR layer and a full vapor blocker underneath it. So there's no way that any kind of moisture vapor is going to get through that insulation, and you only need about 150 mils of it to get that full H1R value. And that's how we're able to cut down on the height of it quite significantly.
Excellent. And again, it's got that, I guess we call it a redundancy layer above that insulation to allow for that drying capacity. So.
Yeah, in this sense, that layer is for kind of water repellency, whereas the vapor barrier underneath the PIR is actually for the air control.
Okay,
yeah.
Excellent. And onto the next part of the H1 calculations, we talked about commercial roofs.
Yep. So these are going to get more popular, is my personal prediction. This is the diamond tri-core system, where you have a metal tray over purlins, and then you've got the high performance PIR insulation. In this case, it's going to be 150 millimeters thick to give you that R6.6. It's actually shooting above it. Then you've got your wrap layer above that to control the dynamics. You've got a batten above that, which actually allows for airflow to stop condensation and also allow for movement. And then you've got your top metal tray. The batten in this case is underrated. It does a lot of things that people don't really appreciate, and it is highly recommended if you're going to go for a system like this. I guess that kind of leads into the next slide. So this is a kind of recent system that has come into the market where lofted insulation is put between two layers of metal. All we can really say about this one is that the airflow is critical for this system. If for whatever reason there isn't proper vapor control of that first tray, and if there isn't good enough airflow under that top skin, there is a high likelihood that there is going to be condensation. And like Jason mentioned earlier, because there's so much insulation on this build, there's not a lot of energy to dry out that space. Despite it being the top skin of a roof, in this example, it's still going to take 2 months to dry out whatever condensation is getting in there. So I guess our message for this one is to just be careful and consider the possible unintended consequences of this build-up.
Yeah, no, absolutely. Obviously, we never actually came to a result on that calculation. Ended up with a question mark there, and it's dependent on so many things. It's dependent on that metal tray underskin being completely airtight to stop that moisture air rising. I haven't seen two sheets of metal flipped over one another to create an airtight seal ever. So something to consider there. So good points all around. All right, so just to quickly summarize what we try to cover today. So we're saying that installing a wrap layer is very important. So that's your water air vapor control layer. No matter what you're doing, that's probably the key takeaway there. It's going to improve your roof performance and reduce your risk. It's going to give you that sort of level of redundancy that you may need because this conditions change and building uses change and things like that. I think even just a simple a repaint of your roof, changing the color, can actually change the way your roof performs in a drying capacity. We've illustrated the airflow above the insulation layer is needed to get rid of that moisture. And also consider thermal bridging. Actually, we've just seen a question come through around about penetration, skylights and things like that. So Peter's software is a simple two-dimensional snapshot. Would that be fair to say of the roof build-ups?
Yeah, and it makes it quite difficult for that last example because they'll have thermal bridges through the kind of metal supports for that top skin, but they're only periodic. The only way I can look at it is one of your materials has to go infinitely one way or another. So there has to be like a continuous line of a purlin or something like that. So skylight penetrations can be quite difficult to consider. That's more like a would-be sort of scenario.
Okay.
Yeah, or a three-dimensional heat transfer model.
Yeah.
Yeah. So I mean, who would do that sort of thing, Jason? Like we just use our. Oh, good on you, man.
We've got a couple of skill folks do that stuff.
Yeah. So we're just using this software just to take a two-dimensional snapshot to get a complete answer. You'd need to engage the likes of Jason, who can do I guess a more in-depth analysis of what we've
trying to build. So
Yeah, although I have to admit that most of the time I do the more in-depth analysis to tell you that you should change the roof so it looks like more like one that Peter can model. A lot of times when you hit complexity, the better thing to do is not to figure out complexity, but just to make it simpler.
Right.
I mean, I love doing complicated
And
stuff.
the other piece of our summary is that we're saying that PR insulation is a very useful way to achieve high insulation value simply because of the great thermal resistance that the PR board provides. So, all right. Sorry, I've got some feedback in my ears there. So that's us. That was us. That was our webinar. That's our summary. Now we've got a few questions from the audience, which is quite good. I like this one, and we shouldn't have assumed everything. What's the schedule method? Great question.
So should I take that one? So
Yep,
in the new and old H1, there's effectively 3 methods you can use to prove that you have sufficient insulation in your building. The first one is a schedule method. So you have to have that. You just say that the R value, you just show that the R values for your walls and your roof and your windows and your floor are above a certain number. And you can do that by just referencing the brand's home insulation guide, which is what most commonly everyone does, or using Design Navigator online, or using a more complicated tool like Passhouse Planning Package or Beckus, right? That's a schedule method. So it's kind of the simplest one. Then there's the calculation method, where you can kind of offset for a certain glazing ratio on homes. You're allowed to say, oh, I'll make the roof a little bit thinner and I'll make the wall a little better. And you can do a simple hand calculation with pencil and show it's good enough, right? And then finally, there's a modeling method. And actually, it's something we didn't talk about because we were just talking about schedule method here.
Yeah.
But in the new H1 code, not the acceptable solutions, but the verification methods, they've got a modeling methodology. And in that, you can basically model a building that's built as per the schedule method, and then a building built the way you're actually going to build it and show that the whole building meets the standard. Because a lot of our certified pass houses in New Zealand, which are much more efficient than the standard is trying to achieve, have less than an R6.6 roof. But they've got much better windows than what's required in the schedule method. So on the balance, they're still much more efficient than the schedule method building. Hopefully I didn't lose any of that.
We may have lost him.
All right, let's keep going then.
We lost Shane.
I'm back.
Well done, Shane. That is an awesome strategy.
I can be in 2 places at once. Sorry about that, folks.
Yeah. So so I think we finished the schedule method question. Yeah, so in the modeling method has changed in H1, the new verification methodologies. But the main change from my point of view is that they now allow the Passhouse Planning Package to be used for that modeling method, which is good because we've got quite a few architecture firms that have that skill set in-house now.
Okay, cool. Thanks for that, Jason. Got a question here for you, I think, Peter. Someone's asking, is the flat membrane warm roof, is it trafficable? Is it walkable?
It's okay for light maintenance traffic. If you're walking on it every day, then it's not acceptable for that. You'd have to put a floating deck on it. Generally, what I find is that if there is a door threshold connected to it, then you need a floating deck.
Yeah. Yep. And I guess that's part of Nuralite's offering as well. We have a full code mark certified trafficable walking deck warm roof solution if you need one in conjunction with our Nurajacks.
Yeah.
I like this question. Can we use a good polythene to use as a vapor barrier instead of an aluminium foil?
You could use a fully adhered vapor tight membrane there, which might include polythene as one of the layers.
Right.
But I wouldn't just use builder's plastic. No.
I have seen issues on site where joining the laps is very difficult.
Yeah.
And I guess nothing is as airtight or as vapor tight as an aluminium foil layer.
It's true, nothing's as vapor tight. That's true.
Yeah.
But there's a lot of fully adhered membranes that would be suitable for that application, but it just depends on the roofing material and everything else. So
yeah, I think that's the reason why your potato chips come in a foil bag now, right?
not a plastic one that's taped together.
Yeah. Right, got a couple. Oh yeah, another question here. What does PIR stand for?
That is a mouthful. That's polyisocyanurate. It's a kind of a foam.
It's a foam plastic. Yeah.
Yeah.
A bit of term.
That's able to have a closed cell structure, and because of that, it has a very high thermal performance value. It's about all there is to that, really. It's got a foil layer to it. Valid?
Yeah, I mean, you could say it's about twice as good as the white EPS foam in your chili bin that you get at Vitaten. Yeah. So it's about, per thickness is about twice as good. It's kind of a good rule of thumb.
Okay. And one last question here before we move on to the next bit. Can PIR be swapped out in a warm roof for rock wool when we're building above height? Short answer, yes, it can. That will give you, it will need to be thicker to achieve the same R value. Also, with our roof build up, we can actually have a hybrid version as well, where we're using a combination of PIR board and rock wool. So talk to us about that. We can do something specific,
The important thing to note is that for walls, you can only use PIR for up to 10 meters. But when you're doing a warm roof, that same restriction doesn't actually exist. So over 10 meters, PIR is okay for a warm roof, just because of the level of containment that it has.
Sure. Okay. All right. I know we're getting close on time. There's lots and lots of questions here. I can't believe it. So what we'll do is we'll answer all those, and they'll be sent back out with the mail out. So just to wrap this up for the end of the year, it feels like the end of the year, that's for sure. It's been a very difficult year, and everyone's had their challenges. It is Christmas, so we want to give away some goodies here. So what we have typically done this whole year with our webinars is obviously we can't come and see you in the office, so we've turned a $10 sort of per head sausage roll budget into a donation. So because it's Christmas, we've upped that to $50 per attendee. So for everyone attending today, we're just going to pop up a poll on where you would like your $50 donation to go to. So you've got some choices there from Kids Can, Women's Refuge, Christmas Box, Auckland City Mission, or Kiwi Harvest. So we'll just leave it up for a minute or two just to let us know where you'd like your $50 to go towards. It says host and panelists cannot vote. Oh, it's rough.
Yeah, I noticed that.
So yeah, by all means, pop that in there. Okay. All right. Well, I think that ends this webinar. Lots of questions for us to go back and answer, and we'll come back to you all on. I don't want to take up all of your time, but Jason, thank you very much for being on the panel again.
You're welcome, and happy holidays.
Yeah, likewise,
Thank you.
And thanks to everyone there for watching. We'll be back next year, no doubt, with more webinars. Very Merry Christmas to you all, and thanks for viewing.
See you guys.